Hello students, I welcome you in today's session of physics. And in physics, I'm going to take your chapter number 15, which is your flow of liquids. Clear? As you know very well, in our previous lecture, we had covered out most of its topic. You can see here, we had covered ideal liquids. Clear? After that, the streamline flow or laminar flow, turbulent flow, critical velocity, or you can say the Reynolds number. Then we had discussed about the viscosity also in our lecture number 1. Now today, this thing we had also discussed in our first lecture, and in now today's class we are going to study about the effective force of a body falling in a liquid, which is your Stokes law. This is the important one, and this thing we are going to discuss in today's class. So when a body or a ball is gently dropped in a liquid, then in the initial stage velocity of the ball is small as in the beginning. The viscous force is negligible. As such, the ball falls with acceleration developed due to the effective weight. Effective weight is equal to how much? Actual weight and the upthrust provided by the liquid in the upward direction. So as a result of this, the velocity of the falling ball goes on increasing. So the layer of water in contact with the ball tends to move with the velocity of the ball, while the layer far away from the ball remain at rest. Clear? So there's as a result of the motion of the ball, there is a relative motion between the adjacent layers of the water. Hence a viscous force is developed in water, which opposes the motion of the ball. So the magnitude of this force goes on increasing with the increasing in the velocity of the ball, and a stage is reached when the opposing viscous force become equal to the effective force driving the ball. So the net force on the ball is now 0, and the ball attains a constant velocity called its terminal velocity. So the viscous force limits the speed of the body falling in a liquid. Now Stokes shows that if a small sphere whose radius is smaller in moving with the terminal velocity v through a perfectly homogeneous medium, liquid or gas, I hope you know very well what is homogeneous and heterogeneous mediums, of infinite extension, then the viscous force acting on the sphere is how much? F is equals to 6 pi neta rv. Clear? This is the force which is acting over the liquid. So this relation is known as Stokes law. So in this formula, neta is the coefficient of viscosity of the medium. Fine? Or you can also set up the relation between neta, or you have to find out the coefficient of viscosity, then you can write it this formula like this: neta is equals to F by 6 pi rv. Clear? This one. Now same thing, if we discuss about the dimension of the coefficient of viscosity, so ml inverse t minus 1. Clear? This is the important concepts. Calculation of the terminal velocity. You can see here from this figure how we calculate the terminal velocity. So let us consider a small ball whose radius is how much? Smaller, and density is rho, falling freely in a liquid or gas whose density is sigma and coefficient of viscosity is neta. You can see from this figure number 6. So when it attains a terminal velocity v, it is subjected the two force. Here you can see that first one is the downward direction and the second force is in the upward direction. So how much is the effective force? Weight of the ball minus upward thrust. Here this is the upward thrust and the weight is acting vertically downward from this. So you can write it v rho g minus v sigma g. Clear? So if you take the common from this term, so it comes out to be equals to how much? In place of v, volume. This is the volume of a sphere is how much? 4 upon 3 pi r cube. Clear? So we put the value of volume, that is 4 upon 3 pi r cube, and rho minus g multiplied by g. And you also know very well a viscous force acting upward, that is how much? This is the viscous force. This is your 6 pi neta rv from the Stokes law I told you. So finally, since the ball is moving with a constant velocity v, there is no acceleration in it, so the net force acting on it must be 0. Fine? So what happened? You can consider this the force 6 pi neta rv is equals to 4 by 3 pi r cube rho minus sigma multiplied by g. Or you can also find out the value of v like this: v is equals to 2 by 9 r square rho minus g rho minus sigma multiplied by g upon neta. So this, the terminal velocity of the ball, this is your terminal velocity, is directly proportional to the square of its radius. Because all these terms are constant, and the total velocity is dependent over the radius of this tube. Fine. Now here are the few applications of the Stokes formula given here. You read it by yourself. If there is any doubt, ask me in the comment section. What are the application? Velocity of the raindrop, parachutes. Clear? Now I am moving to the flow of liquid through pipes, which is your Poiseuille formula. This is also important. So pay attention, students. What is Poiseuille formula? You can see here from this. So experimentally, it can be shown that the volume of a liquid flowing per second, that is the rate of discharge through a pipe, depend on which terms? First one is the viscosity of the liquid, and the second one is the radius of the pipe, and the third one is your pressure gradient. Pressure gradient means pressure per unit length, is known as pressure gradient. So the method, the using method of the dimension, we can write the formula Q is equals to V by T is proportional to these terms, where K is the constant, and after solving out all these terms, we can see here we are finding that the dimension, finally the relations comes out to be this: pi p r to the power 4 8 neta L. So this is the relation known as Poiseuille relation. So kindly remember this relation, it is important one. So with the help of this formula, the viscosity of a liquid can be determined. Clear? So rearranging equation second, you can see here, where is the equation number 2? This is equation 1 second. Fine. Sorry, this one is your equation number 8, which is your Poiseuille formula. So you can rearrange it, and the finally relations comes out to be like this here. So now if it is compared with the well-known equation of current electricity, that is Ohm's law, V is equals to IR. I hope you know very well the Ohm's law, V equals to IR. Then what happened? We find the term 8 pi neta L, pi r to the power 4 is equivalent to the R. Clear? So this term is known as the viscous resistance. So how will you define the viscous resistance? So R viscous is equals to 8 neta L by pi r to the power 4. This is your equation number 3. So the equation 3 shows that the viscous resistance increases with the increase in the length of the pipe and with decrease in its radius. It is also dependent on the coefficient of viscosity increases with increase in the viscosity of the liquid. For example, you can see here glycerine offer more resistance than water when flow through a pipe. I hope you understand it. Now come to the principle of continuity, which is your topic number 11. What is the principle of continuity? It states that when an incompressible and a non-viscous liquid flow in a streamlined motion through a tube of non-uniform cross section, then the product of the area of cross section, clear, and the velocity of the flow of liquids is same at every point of the tube. This is the definition or principle of continuity. So now we are proving what is the principle of continuity. This is your important one. You can see here, this is the figure. Here you can see in the figure, let us consider a liquid which is flowing in a streamlined motion through a non-uniform tube xy. So let A1 and A2 be the cross-sectional areas of the tube, and V1 and V2 with the velocity of flow at x and y respectively. We are supposing that rho be the density of the liquid entering from which place, you can see here liquid entering at this point, which is x, cover a distance v1 in 1 second. Fine. Thus the volume of the liquid entering at the end x in 1 second, you can see that a1 multiplied by v1 multiply its velocity. So the mass of liquid entering at the end x in 1 second is how much? Rho multiplied by a1 v1. Similarly, the mass which comes out from the end d is equals to a2 rho multiplied by a2 v2. So but the liquid which enter one end must leave at the other end, and both the masses are equal. So if we compare this one and this one, so we can write it this formula: rho a1 v1 is equals to rho of a2 v2. So rho and rho are cancelled out from both the sides, and finally you can see here a1 v1 is equals to the a2 v2, and finally a into v is equals to the constant. So this is the principle of continuity. So that at every place in the tube, the product of the area of cross section of the tube and the velocity of the flow of liquid is constant. Therefore the velocity of liquid is smaller in the wider parts of the tube and larger in the narrower parts. This is the important. Now here you can see what are the different energies in a flow of a flowing liquid. So I hope you know very well what are the energy. First one is your pressure energy, Second one is your kinetic energy, third one is your potential energy. You can see the relative formula pressure, and this is one is your kinetic energy formula, and this one for the potential energy formula. Clear? Now come to the Bernoulli's theorem. This is the most important topic of this chapter, Bernoulli's theorem. Clear, students? Now what's the Bernoulli theorem states that? Says that when an incompressible and a non-viscous liquid or gas flow in a streamlined motion from one place to another. I hope you know very well what is streamlined motion. I told you in the lecture number 1. So at every point of its path, the total energy per unit volume, pressure energy and the kinetic potential energy is constant, and this is the formula for the Bernoulli's theorem. P plus half rho v square plus rho gh is equals to the constant. Fine. So you can see here, thus Bernoulli's theorem is in one way the principle of conservation of energy of the flow of liquid. This is important one, kindly remember. Bernoulli's theorem is based on which principle? So it is based on the conservation of energy. Clear? Now here we are going to prove the Bernoulli's theorem. So from this figure you can see here, this is the figure for the Bernoulli's theorem. Prove suppose an incompressible and the non-viscous liquid flowing in a streamlined motion through a tube XY of non-uniform cross section. Figure number 10 you can see here. Let suppose us that A1 and A2 be the area of cross section of the tube at the end X and Y respectively, which are at a height of H1 and H2. Fine. So from the surface of the earth we are supposing that P1 be the pressure and V1 the velocity of the flow of liquid at X, and P2 the respective quantity at Y. Since the area A2 is smaller than A1, the velocity V2 is greater than V1. So principle of continuity, according to the principle of continuity, the liquid which enter at X travel a distance V1 in 1 second on this liquid is acting a pressure of P1 multiplied by A1. Now what the work done per second on the liquid entering the tube? So you know very well, force is equals to force into distance, which is your W is equals to F into D. Clear? So we can write it force into distance, so P1 A1 multiplied by V1. Clear? And similarly the work done per second of the force P2 A2 by the liquid leaving at the end Y. So we can write same thing, P2 multiplied by A2 multiplied by V2. So the net work done, if you find out the net work done, so what can we do? You can see here we find the net work done on the liquid P1 A1 V1 minus P2 A2 V2. Fine. But A1 V1 and A2 V2 are respectively the volumes of the liquid entering an X and leaving at Y per second. So these volume must be equal to A1 V1 is equals to A2 V2, which is m by rho. Now what is m by rho? M is the mass of the liquid entering at the X end and leaving at the Y end in Y second, and rho is the density of the liquid. So substituting these values in equation first, in the above term, if you see the equation, this is your equation number 1. So you will get the net work done P1 minus P2 m by rho. Now you know very well what is the kinetic energy of a liquid which is entering in the X is half mv square. So this is the kinetic energy, and the liquid Y leaving in 1 second half mv square. So increase in the kinetic energy, you can write it, this is the change in the kinetic energy, half m v2 minus v1 square. Now the potential energy of the liquid at X is mgh1 and at Y is mgh2. So the decrease in the potential energy, you can find it mgh1 minus h2 here. And the net increase in the energy of the liquid, half mv2 square minus v1 square, or minus mgh1 minus h2. So the increase in the energy due to the net work done on the liquid, so net work done is equal to net increase in energy. So equation second and third, here you can say this is the third equation. Finally we can write it P1 minus P2 by m by rho, half mv2 square minus v1 square minus mgh1 minus h2. Or you can write it P1 minus P2 half rho v2 square minus v1 square minus rho g h1 minus h2. Finally, if you rearrange all these terms, you get this relation equals to this. So after that you can write it P plus half rho v square plus rho gh is equals to constant. So this is the Bernoulli's theorem. This is the most important one. So kindly solve this derivation twice and thrice. Now here you can see that there are the few discussions of the Bernoulli's theorem: pressure head, velocity head and the gravitational head of the flowing liquid. So if they divide the above equation by rho g, so what we get, you can see here P by rho g plus V square by rho g plus h is equals to constant, where p upon rho g is called as pressure head, v square upon 2g of the velocity head, and h is the gravitational head. So this is also the important, what is pressure head, gravitational head, and velocity head. I hope you understand it. So the dimension of each of these three is the dimension of height. So the sum of these is called the total head. Clear? It means if we sum all these terms, so it is called as the total head. Therefore, Bernoulli's theorem may also be stated as, in a streamlined motion of an ideal liquid, the sum of pressure head, the velocity head, and the gravitational head at any point is always constant. Fine? Now you can see here, when the liquid flow in a horizontal plane, that what happen in that case, both the heights are equal. So in that case, you can see here this the relations changes like this. So P1 plus half rho V1 square equals to P2 plus half rho V2 square, and P plus half rho V square is equals to the constant. It means that the horizontal streamline motion of a liquid, the pressure, the sum of the pressure and the kinetic energy per unit volume of the liquid at any point is constant. So it is clear from the equation of Bernoulli's theorem that in a flowing liquid or a gas where the velocity of flow is less, the pressure is larger, and vice versa. So if a liquid is allowed to flow in a tube which is narrower in the middle, clear, then in this part the velocity of the liquid is greater and the pressure is smallest. I hope you understand it. There are the few applications based on the Bernoulli's theorem. You read it by yourself. If you have any doubt, ask me in the comment section. What is the Venturi meter and what is the working principle? This is same as I already told you. And the shape of the wings of an aeroplane, this is also the example of based on the Bernoulli's theorem. So read it these example by yourself, and if you still have any doubt, you can ask me in the comment section. What is the Bunsen burner? Clear? Atomizer. These are the few all the example of Bernoulli principle, Bernoulli's theorem. So I am skipping all these examples. You can read. This is the most important one, Magnus effect. Clear? So you read it properly. Magnus effect. What is the Magnus effect? Fine. After that, you can see that the velocity of efflux of a liquid, or Stokes Law theorem. We will discuss this Stokes Law theorem in our next lecture, which is lecture number 3. Clear? Till that, students, do study. Thank you, class. Thank you very much.